Hello everyone. I chose a projectile motion problem for my project. And if anyone's ever seen the movie Anchorman, you know the scene where Jack Black drop kicks the main character's dog, Baxter, off of a bridge. So I wanted to calculate, hypothetically, how far this dog could go. So I went ahead and drew this little picture beforehand to kind of represent, but I'm going to go ahead and explain. And we have our known values here that I'm going to show on the side of it. Bear with me here. I'm not using my typical program as I have lost my good pen, so I'm using Canva. Anyways, so we start off with our origin point, which I have highlighted in green over here, but I'm going to go and circle again. That's telling us where Jack Black's foot made contact with the dog and he went flying, right? So I just made up these values, obviously, because it's a made up problem. That represents both our y naught and our x naught. So our x naught, as usual, is going to be 0 meters. My y naught, I used the reference of sea level, so I drew like a little C here. And from sea level, the point of contact is 40 meters up. In this case, I said that the dog was kicked at a velocity of 15 meters per second and at an angle of 55 degrees. So we know all these values from, what I was given in the equation. The ones that can be inferred are the acceleration due to gravity, which is a constant, so we know it's always going to be negative at 9.8 meters per second squared. I personally find it easier to do the negative, but that's just my preference. I also drew this helpful little diagram here so we know the x and the y direction, and the general pathway for the trajectory, which can be followed along here. So we can also know that since this is a projectile motion problem, there's no forces acting upon it in the x direction. So normally you'd have the force equals mass times acceleration. Since the net force in the x direction is 0, we know that the acceleration also has to be 0. So 0 meters per second squared. And then we have finally, we want the dog to be landed at sea level, and we use the reference of sea level here. So we have y final equals 0 meters. So now, where do we start here? Well, we know that we want to solve for x final, right? Solving for x final is a bit tricky, but I wanted to do it because I felt like it was good practice here. So we have our equations that we need to use. We don't yet know our v naught x and our v naught y. So that would probably be my first step, just so that I have those in my known. So your v naught x is equal to v naught cosine of theta, and v naught y is equal to v naught sine theta. So from here we can add these to our tables of known values, because we plug in our 15 for our v naught and cosine of 55 here, which in this case I got v naught x equals 8.6 meters per second, and then our v naught y is 15 sine of 55, and for that I got v naught y equals about 12.3 meters per second. So that kind of gets those out of the way so we don't have to remember to go back and do them later. But we want to find an equation that's going to solve for xf. And in this case, we have our equation of x naught plus v naught y t plus 1/2 a t squared. We're going to come back to that, though. We're not really going to touch that entirely yet because we also don't know our t, and that's an important thing that we're going to need to solve. So in order to find our t, we have to find another equation that we know all of the values for that t is also in. So in this case, we can't do that yet, my bad. We also have our equation for y final, which we know all of the values for, right? Because we have y final equals y naught, supposed to be not, plus v y t. We know everything except for t, obviously, plus 1/2 g, not a, because in this case the g is acting down in the y direction, g t squared. So this is what we're going to want to use to solve for t. Now, you might be thinking, well, how can we do that? Because we have t in two different terms, and they're not the same, right? Because this is regular t, this is t squared. Well, when you look at the equation for, or the general pathway for the y direction of an object, right? We had our trajectory here, which solves for our y. So I'm going to kind of move that over to just a separate graph to kind of make that visually easier. So we have our graph of our y versus our time. So in this case, we know our y starts at 40, and it has to end wherever it meets the t here. So this is where y equals 0. We don't know what t equals at this point. And because it is a quadratic, we have that value of the t squared. My bad, that's supposed to be 2. The t squared, and a regular t, and just a regular number, correct? We're going to have a general parabola type shape. So I don't know why it's not letting me move that. A general parabola, right? We cannot have a negative time, so we're going to ignore wherever the graph would meet this axis on this side, just focus on solving for this value of t here. So in order to do that, we're going to take this equation. I'm first going to kind of rewrite it to make it a bit clearer. So we have our yf. We know that yf, actually before we start that, we know that yf is our only 0 in this equation, right? Because it starts, or we want it to end at sea level, we want it to end at 0. We want to solve for t when y equals 0. So that's kind of going back to our quadratics and our algebra and pre-calculus. So we have to have our 0 and set it equal to this 1/2. We're going to rearrange that so that the exponents are in order. I just find it personally easier. gt squared plus b naught yt plus y naught. Now that we have this rearranged, we're going to plug in the values for g and v naught y and y naught, because we want it to kind of look like our regular quadratic formula, which is 0 equals ax squared plus bx plus c, in the case where our x's, in this case, are t's, right? And you can see the formats really do match up once you plug in the real numbers. And you're going to get what your a value will be, what your, let's do different colors for that, what your b value will be, and what your c value will be in order to solve that equation. So I'm going to go ahead and plug in these values here and do out some of this math. So we have our g, we know, equals negative 9.8. We're also going to multiply that by 1/2. Excuse me. We're going to have negative 4.9 t squared plus our v naught y, which was 12.3 t, plus our y naught, which was 40. Now we have our a value, our b value, and our c value. And now, we're going to plug that into the quadratic formula, which is t, in this case, normally it's x, equals negative b plus or minus the square root of b squared minus 4ac. Put that all over to a. And I know you're probably thinking that this looks like a jumbled mess, but once we plug in the values, it gets a lot easier, especially considering the fact that we know t has to be greater than 0. So now we're going to plug in our values here. So we have t equals negative our b value, which was 12.3. And then we're going to move this over. Negative 12.3 plus or minus the square root of 12.3 squared. It's supposed to be a 2. I'm going to zoom in a bit. Squared minus 4 times negative 4.9 times 40. And put that all over to times 4.9. So now I'm going to solve for the radical. You can go ahead and do that by yourself too. I just found it easier to type all of that into a calculator. So we have t equals negative 12.3 plus or minus the square root of, ended up being 935.29 all over 2. Keep doing that. Well, we have our 2 times 4.9 here, which gets us back to that 9.8. So now we're going to take the radical, we're going to solve for that. And we know that both the top and the bottom have to be negative, right? Because we can't have a negative time. So we want that to cancel out into a positive number. So we have our negative 12.3. We're going to have to subtract whatever we get for the radical here, which is 30.58. Now we have t equals something over negative 9.8. We go ahead and we subtract these two values to get t equals negative 42.88 over 9.8. Now, these two negatives are going to cancel, and we're left with, and we have to solve for that, so we're left with t equals 4.376 seconds. Cool. Awesome. So that tells us now exactly how long this poor dog was flying through the air, right? So we know that his trajectory time, we can now write, that's big. We can now write that his trajectory time is equal to 4.376 seconds. We can also put that into our knowns table if we really need to. T equals 376 seconds. But we're not entirely done because we wanted to know what xf is equal to. Now that we have our t, we can go back to this equation right here. We're going to go ahead and take that equation and solve for our x final, which is pretty easy because it's already on its own side of the equation. We have our x final equals x naught plus v naught x t plus 1/2 a t squared. Now we're looking at this, and we can determine any zeros. So we know our x naught, our origin point, is 0 in this case, so we can get rid of it. We also determined earlier that our acceleration in the x direction is equal to 0, right? Because there's no other forces acting upon it. So this whole term can be canceled out. And we're left with xf equals v naught x t. And that is super easy to solve now because we have our values for v naught, x, and for t. All we have to do is plug them in. So we have xf equals the value we got for v naught x, which is our 8.6 meters per second. 8.6 times our t, which is our 4.376. Multiply those together, and you get xf, or x final, from the origin point, not from the edge of the bridge. I'm going to make that clear. I was going to originally have it from the edge of the bridge, but from our origin point here all the way over, our x final, where is that here, is going to be equal to about 37.636 meters. And there you go. That is how you solve for that problem. Thank you. Have a great day.